Good day everyone, my name is Nur Raihana Sukri. I am from Malaysia Japan International Institute of Technology, University Technology Malaysia. So today I will present a review of structural damage identification using model updating approach. First of all, I have a question to ask. Have you heard about finite element model updating? No? Don't worry. This presentation will give an introduction to structural damage identification and information on finite element model updating. Therefore, at the end of this presentation, you will get a brief idea about model updating and its application in structural damage identification. I divided this presentation into 5 parts. The first part is for introduction. In part 2, I will give a brief description of the finite element model updating approach. Section 3 is dedicated for the structural response. Then I will share trends in recent case study in section 4. And finally, last part is for conclusion. Structural damage is a long-standing challenge for the engineering community because deterioration of the structure will badly affect its safety and reliability. Damage can be described as any difference in the structural physical properties or material properties that may cause unwanted stress, displacement, or vibration on the structure due to several factors such as corrosion, fatigue, and cracks. Hence, different types of damage affect different structural properties. Therefore, structural damage detection plays an important role in the early damage stage. The purposes of structural damage identification are to identify, locate, and distinguish the structural damage. There have been numerous studies to investigate structural damage identification. Songs et al. Classified the methods of structural damage identification into local methods and integrated methods. The local method is a non-destructive testing, while the integrated damage identification methods are based on structural vibration. The integrated damage identification methods are then divided into model-based and non-model-based methods. Model-based methods use characteristic values related to structural models, including the natural frequency, mode shifts, model curvature, dynamic flexibility and dynamic stiffness, and the finite element methods to identify the damage. Non-model-based methods use characteristic values derived from the vibration time history, frequency spectrum, or time region instead of feature of the structural model. Researchers over the last decades have studied various model updating techniques for structural damage detection. Model updating technique can be loosely described as model calibration, where this technique is basically about updating a finite element model of a structure to reduce the errors between numerical and experimental results. There are two categories of model updating technique, the direct and iterative method. As mentioned earlier, model updating techniques can be categorized into direct method and iterative method. The iterative method consists of sensitivity-based methods, probabilistic or statistical method, optimized algorithm methods, and evolutionary algorithm method. The direct method requires complete modification of the system matrices or substructures. Some examples of direct methods are error metric methods, metric update methods, optimal metric methods, and the eigenstructure assignment methods. The sensitivity method is based on linearization of the generally nonlinear relationship between measurable outputs and the parameters of the model in need of corrections. Researchers in the iterative method extensively use modal data-based methods and frequency-based methods. Model updating can also be done by using statistical and probability-based approach. Bayesian framework-based method, Taguchi-based method, and Tikhonov regularization methods are examples of this approach. Aside from the methods mentioned earlier, Researchers have examined various optimization algorithms to solve the finite element model updating problem. The optimization algorithm can be used directly or combined with the sensitivity-based method depending on the ability of the optimization algorithm to handle complex and highly nonlinear finite element model updating. Examples of optimization algorithms are Nelda-Mead, couple local minimizer, trust region Newton, penalty function, and sequential quadratic programming. The evolutionary algorithm is a computational intelligence technique used to solve complex optimization problems. Tug-of-war optimization and Bayes algorithm are examples for evolutionary algorithm methods. The benefits of using direct methods are computationally cheaper and it shows precise results. However, Al-Qayyum et al. Stated that the direct method might not give a reasonable physical explanation of the changes in structural characteristics. Meanwhile, the iterative method, or also called as sensitivity methods, overcome the limitation of the direct methods but requires a sensitivity matrix concerning all updating parameters, leading to expensive computation. This method may not apply to structures with considerable damage, but it is applied successfully to large-scale industrial problems. Sipan et al. Emphasized that probabilistic or statistical method provides detailed information about the uncertainty of the quantities of interest. However, this method is computationally demanding and challenging because one needs to understand the distribution of all variables. Optimization algorithm minimize residual between the dynamic characteristic of the finite element model and the image structure. Despite the success of the optimization algorithm in certain aspects, it is still suffers from low efficiency and failure to solve optimization problems. Evolutionary algorithm can solve complex optimization problem of high nonlinearity, multimodal interaction, but the application to structural damage identification is not yet well resolved. Several studies have examined the structural response for model updating, especially the modal-based and frequency response function-based. The model-based model updating methods depends on the model characteristic data, such as natural frequencies and mode shapes extracted directly from the measured FRF data. Meanwhile, the FRF-based updating method directly employed the measured FRF data to update the structural parameters. PSD is a second-order transfer function where excitation at a certain degree of freedom at each frequency points will lead to the auto-spectral and cross-spectral density of the responses. This table summarizes the measured parameter used in recent research studies, complete with the model updating method used for each case studies. Researchers number 57, 60, 84 until 92 employed model data for their case study. In contrast, researchers number 80, 94 and 95 have further developed FRF data for 2D structures. Meanwhile, researchers number 81 and 82 developed a sensitivity-based damage detection method using power spectral density. This approach had been tested for concrete beam, plate and shell models. Instead, Young et al. Proposed a modal strain energy-based model updating method for damage assessment of beam-like structure. MSE is defined as the second-order derivative of mode shapes. Besides the modal parameter above, Abrahamian et al. Performed a series of experiments using time-invariant model parameters to a bridge, pier and a moment-resistant steel frame. For conclusion, this paper has listed the numerous techniques for finite element model updating and the advantages and limitations of each method as well. This study showed that researchers in the iterative method extensively use modal data-based methods and frequency-based methods. However, there is an increasing need and scope for the evolutionary algorithm as their application to identify structural damage is not yet well resolved. The insight gained from this study may be helpful for those who want a brief idea of the finite element model updating. Thank you so